This is 48 G bang. This is 48G1, and this is the second part of our section on the laws of motion. So in this part we're going to actually look at two things. We're going to look at equilibrium, which leads to statics, and we're going to look at non-equilibrium, which leads to dynamics. And we'll do a variety of problems on each of those. At the very end we'll talk about apparent weight, which is a little bit of an addition. So lots of problems in this, lots of examples in this tape. So basically when we talk about equilibrium and non-equilibrium, we can say, well, if the sum of the forces, net external forces of course, equals 0, then when an object experiences a net force of 0 newtons, the acceleration of the object is 0, and the object has a constant velocity, which could be 0, it could be stationary. For non-equilibrium, that is dynamics, we say the sum of the forces is equal to ma. When an object experiences a net force that is 0 newtons, the acceleration of the object is not 0. Bang. For non-equilibrium, which is dynamics, the governing equation is that the sum of the net external forces equals ma, and we can say when an object experiences a net force that is not 0 newtons, the acceleration of the object is not 0, and the object has a changing velocity. So let's look at some examples of these. Let's start off with equilibrium, which leads to statics. Here's a classic example. We have a mass, for example a traffic light, is often the example, held up by two strings. There's a string to the right and a string to the left, and we call the tension in the string to the right T right, and we call the tension in the string to the left T left, and you're usually given some angles to think about, etc. And I want to go through with you 3 ways to solve this problem. There's one way, which is using a vector diagram and a scale. There's one way, which is using a scaled vector diagram. And there's 2 ways which involve trigonometry. And for my personal class, I will pose a question in a test which says, using the method of scaled vector diagrams for one question, and I will pose as a problem in a test using the method of trigonometry as another problem. Let's begin by doing the scaled vector diagram. I can't draw it here to scale very well because I don't have a ruler, but I can give you the idea of it. The basic idea is that if this thing is in equilibrium, then the weight and the tension in the right hand string and the tension in the left hand string must sum to 0. Because if there is a gap, if there is a resultant, then the sum of the forces do not equal 0. So the way you could do this is we could recognize that this is 30 newtons, so we'd draw a scale and we'd have 0, 10, 20, 30, and this would be my FG vector. And then the second section we draw is our T right. Now I don't know how long T right is, but I do know that it has a specific direction, which is 30 degrees above the horizontal. If you look up here at this side, it's 30 degrees elevation above the horizontal. So I can draw a horizontal line onto the end of my FG arrow and get a protractor and measure 30 degrees up and draw myself a line. I don't know how long that line should be, but I know that that's the direction that the force must act in. I don't know how long the T left should be, but I know that it has an angle of 40 degrees with respect to the horizontal. Now, what might not be so obvious if you think about it, until you think about it, is that that represents a line which goes down to the right. The arrow is going to point towards the top left, just like it does here, just like it does here, but I got to measure my angle from the horizontal, so that's 40 degrees and that's 30 degrees. Now I can say that the T right should stop at this intersection, so this is T right, and I can measure the length, and I can say that T left should stop at the end point there, and that is T left. Now, how long is that? So let's imagine this is where I need a ruler. I need a scaled ruler, but you'll get the idea. So using my rough measurement, I could say that I think that is going to be 10 newtons, 20 newtons, 20 and a bit newtons. I'd say high 20s. So I'm going to take an educated guess there at 27.65 newtons. This guy here is 27.65 newtons. I didn't get that from my diagram. I got the rough value from my diagram. The bigger the diagram that you draw, and the more careful you are about aligning the arrows correctly, the better the outcome of this method will be. So let's recap. The principle is the force of the weight and the force of the tension in the right hand string and the force of the tension in the left hand string must sum to 0 because the traffic light is not accelerating in any axis. So if I draw these vectors head to tail, which is the process of addition in a vector diagram, then they should form a closed triangle. I know the length of the weight vector, and I know its direction is down the page. I know the direction of T right relative to the page. I know the direction of T left relative to the page. I draw those two axes in. Where they cross tells me the length of T right and the length of T left. I can then use my ruler and measure the value using the scale that I used to draw the first vector. So there it is. It's a nice, simple method. It needs practice, but it works quite well. Let's do the same problem using trigonometry. So I'm going to erase. Bang. Let's do the same problem using trigonometry. And so I have my downwards force, which is 30 newtons. And then I have my T right, which is at 30 degrees above the horizontal. And I have my T left, which is at 40 degrees above the horizontal. Now, for the method of trigonometry, the traditional way of doing it is that you divide things up into horizontal and vertical axes. And what you say is the object is not accelerating in any axis, so there's no acceleration along the horizontal axis, so I can say the sum of the forces horizontally is equal to 0. And so I need to visualize my horizontal components of T right. which I see there. And remember, the original vector t right is always the hypotenuse. So I can say that this length here is t right cosine 30 degrees. And I can envisage bringing down t left and imagine the horizontal vector. And this is t left cosine 40. And then the only thing I have to do is recognize that one side must be in a positive direction and the other side must be in a negative direction. It doesn't actually matter which way round I put the positive and the negative, as long as I'm consistent. So I say, well, plus tr cosine 30 added to, because it's a summation, minus TL cosine 40 is equal to 0. Let's rearrange that a little bit. Eventually I want to find T left, and the trick you learn is that you isolate the thing you don't want in the first equation. So I'm going to say TR is equal to, take this to the other side, TL cosine 40 over cosine 30. Some people like to leave these things as trigonometric functions, and other people like to turn these things into numerical values as quickly as possible. If you do, make sure you leave yourself I'd say 3 or 4 decimal places so that you don't get a rounding error that you could avoid. I'm going to leave them as they are. The next thing I do is I say, well, okay, I need another equation. 2 equations are required when you have 2 unknowns. So I'm going to go to this side here. I'm going to say, well, the sum of the forces vertically are equal to 0, because the object is not accelerating vertically either. And I envisage this vector here, which is t right sine 30. Now, if that is a problem for you to find, if you kind of just look at it and write down that function, then practice, because that shouldn't be what holds you up. And if I take the t left and I again imagine the component, I've drawn these the same length, it's not a big deal. I'm going to put this up here. This would be t left sine 40. This is a positive end and this is a negative end of my axis. I say, well, the sum of the forces vertically, t right sine 30, that's going to be a positive, added to, because it's a summation, t left sine 40, added to, because it's a summation, minus 30, negative because it points downwards, is equal to 0. So t right is equal to, well, it's going to be 30 minus t left sine 40 divided by sine 30. Take that to the other side, subtract that from it, rearrange. Now, as my final step, I take my trying to find t left. Knew there was a problem. Bang. Rearranging this gives t left, which is what I want to find, is equal to 30 minus t right sine 30 over sine 40. So I took my 30 to the other side, it became a positive. I took my t right sine 30 to the other side, it became a negative, and then I divided all the other side by sine 40. As a final step, I can say, oh, t left is equal to 30 minus, rather than t right, I can say t left cosine 40 over cosine 30 times sine 30. I just substituted in for that t right, all over sine 40. And I understand if that looks complicated, but with practice you realize that that cosine 40 is just a decimal somewhere between 0 and 1, and that cosine 30 is just a decimal between 0 and 1, and the sine 30 is just a decimal between 0 and 1. These things they're just fractional decimal numbers. So this would be 30 minus, and I get my calculator, and I first of all I make sure I'm in degrees rather than radians. Sometimes you'll be in radians, and I say that's going to be cosine 40, enter, times sine 30, enter, divided by cosine 30, enter. And that comes out to be 0.4423 TL divided by It's the second time I've done this. Bang! Now, the problem with this equation, of course, is that we have t right still in it. So let's substitute in for t right. So we would say t left cosine 40 over cosine 30 times sine 30 plus t left sine 40. Let's take this minus 30 to the other side, equals 30. Let's gather together all the t lefts, so we can say so now the last bit is we want to go from having these trigonometric functions to having decimal numbers. To my mind, although it looks complicated, cosine 40, sine 30, cosine 30, sine 40, looks complicated. They're just numbers that are between 0 and 1. And if we see them like that, then they're not so daunting. So I get my calculator, and the first thing I do is I check to see that I'm in degrees, because sometimes in physics and engineering you'll be in radians rather than degrees. I'm in degrees. And then what I do is I say, well, cosine 40, so cosine 40, enter, times sine 30 times sine 30, enter, divided by cosine 30, enter. And this is going to equal 0.4423 TL. and then we're going to add on to that. So let's clear, and we're going to go sine 40. So sine 40, and this is going to be 0.6428. 6428 TL is equal to 30. If I add these two numbers together, I have 0.4423 added to 0.6428, enter, and I get 1.0851 TL is equal to 30. So TL is equal to 30 divided by 1.085, which equals, so I'm going to go second inverse. I'm going to go, and so I'm going to go 30 divided by 1.085, and I'm going to get 27.65 newtons. And I can see, yeah, that's the choice I had picked from my previous attempt using the vector diagrams. But this is actually working it out with that precision. So effectively I have two unknowns in this calculation. I have t left and t right. I'm only required to get one of them, which is t left. Because I have two unknowns, I need two equations. Because I have two equations, I have to do some rearrangement. My advice is always so there we have it. So now I'd like to show you the second way using trigonometry, and I need a good diagram for this. So I'm going to lay out my diagram with a little bit of extra care. I know that the force downwards is 30 newtons. I know that this angle to the horizontal for t right is 30 degrees, and I know that the angle for t left is equal to 40 degrees. It's a good idea when you first begin to actually get a protractor and actually measure those properly, because this is where it really matters. Philosophically, I'd like to set up an equation which only has one unknown, and that means that because I want to find t right, I have to set up an equation that can ignore t left. And the way you ignore a force is that you pick the angle upon which you pick the axis upon which the force has no component, and the force has no component on an axis to which it is 90 degrees orientation. So if I pick an arbitrary force and I pick an axis, I can see there's a component here, and I can see there's a component there. But if I pick the axis that is at 90 degrees to the force, then there is no component. So if I can draw the axis which is at 90 degrees to t right, I can ignore it. And the way I do that is this. I say, well, my t right is 30 degrees above the horizontal, so this axis must be 30 degrees beyond the vertical. Can you see? I'm taking that same 30 degrees, and I draw myself an axis. So that's the best way to do it. You say, well, I'm 30 degrees above the horizontal, so that means my axis must be 30 degrees beyond the vertical. Oopsie-daisy. Let me draw that back in. And now, when I say the sum of the forces along the red line equals 0, the forces I'm talking about are the TL, which is what I want, and the 30, which I know. The T right is not included in this equation. It still exists, but it's not included in this equation. So I have to be able to do my components, and again, the TL is the hypotenuse. I know that it's 40 degrees from the horizontal to TL, and I know it's 30 degrees from the vertical axis to my red line. 40 and 30 makes 70. So I know I have 20 degrees between TL and my axis. So I know that this component is going to be TL cosine 20. So there's a bit of geometry there. I have to be able to work out what the angle is between TL and my axis using geometry. It needs a good diagram. If I look at the 30 Newton, again, the 30 Newton is the hypotenuse. So I have the component of the 30 Newtons along the red axis, and that's going to be 30, and it's going to be cosine, and the angle is going to be 30 degrees. And the reason I know the angle between the weight and the axis is 30 degrees because the vertical line is projected and the red line is projected. If they're 30 degrees on this part of the diagram, they're 30 degrees on the other part of the diagram. The final bit I need to remember is that one end of this has to be a positive end and the other end has to be a negative end, and again, it doesn't matter which way around I do it as long as I pick one. So I say the sum of the forces along the red line, it's going to be positive TL cosine 20 added to negative 30 cosine 30 equals 0. So rearranging, TL is equal to 30 cosine 30 divided by cosine 20. So this equals, let's get our calculators, check you're in degrees, 30 times cosine of 30 degrees, enter, divided by the cosine of 20 degrees, enter, and this equals 27.65 newtons. So, using trigonometry, there's the brute force way, the traditional way, which is using horizontal and vertical components, having two unknowns in each equation, and then solving because you can solve two unknown problems having two equations. Or alternatively, you can solve this with one equation by picking the axis which enables you to ignore T right. There's more geometry, but there's less trigonometry. And both give you the right answer, and as far as I'm concerned in my class, for the first test I don't mind. For the first time this comes up, I don't mind. People can do it the trigonometric way using 2 equations or the trigonometric way using 1 equation. But I would point out to you the fact that by being shrewd about the positioning of my axis, I saved myself a lot of work. And so throughout physics and later engineering, we find that there's often a brute force way of solving things, and then there's a simpler way of solving things, because we take into account some insights based on the geometry of the situation. So by all means do it the brute force way, but don't be close to the second way of doing it. I'm going to pause there and then we'll do some more examples.